All right, everybody. Hello, welcome back. Happy 4th of July. I'm wearing my Pentagon t-shirt today because 4th of July weekend just happened. Anyway, today we have a lot to talk about. I guess I have a lot to talk about. We're gonna do the compressor. This is compressor and more. So let me start. A lot to cover today. I try to make it quick. Alrighty. So five type of compressors I'm gonna cover. The reciprocating, scroll, rotary, I will cover. Semi-hermetic in details. Centrifugal and screw, I will not cover, just a quick video. Alrighty, then I'm going to also go with oil control, supermarket oil diagrams, capacity control, compressor pump down. That's how we check if it's broken or not. I'm going to talk a little bit about atmospheric pressure and elevation, standard versus high efficiency. That's system. Unloaders, two types. Compression ratio. I talk about the compressor starters, the potential relay, current relay, PTCR, 3-in-1, and universal relay. Of course, we're going to talk about troubleshooting electrical. We're going to talk about the problem versus the cause, 4 causes of failure, of compressor failures, and one more, Robby's 4 causes, the books that mentions 4. There's one more, of course, I will talk about it. And of course, a lot of Robby stories. Alrighty, so the compressor, let's get started, rock and roll. The compressor is the heart of the system, ready? It's a vapor pump, does not pump liquid. People think the pump is liquid vapor pump. It's a pressure increaser from low to high. And it's suction cooled, cooled by the suction line, except the rotary is vapor cooled. And the compressor have one main job is to suck, compress, and discharge vapor refrigerant. Similar to the human heart, but the compressor are vapor pump. Alrighty. So 5 types of compressors. Cool. The rotary, which is half to 5 horsepower. They have less than half. Some things are wrong. They also have the mini tiny rotary. Or we have the single, twin, and triple rotary. Now we have the mini one. I like to put it in there. It's nice. I saw this in Vegas at the convention. Small, little, tiny, awesome. All right, it goes to 1.34 horsepower. So, 746 watt is 1 BTU. So we do the math, and that's how we figure out the size. Alrighty, let's move on. We have the reciprocating, pistons go up and down. And we have the reciprocating, we have the hermetic, semi-hermetic, and open drive. The open drive is semi-hermetic. Alrighty. And the reciprocating, they go from an 1/8 horsepower to 3 horsepower for domestic refrigerator, chest freezer, small reach-ins, and air conditioning too, I guess. Let me go back. Air conditioning also. Alrighty, let's move on. As the now we have the semi-hermetic. Semi-hermetic is from half to 50 horse. You're not going to see this in residential, it's for commercial. And we have the hermetic, open drive, and hermetic and open drive. Now we have the scroll. And it goes from 2 horsepower to 30 horse. The screw compressor, I'm not going to cover much, 25 to 100, but I do have a story about the screw and pictures. And the centrifugal is for major stuff. I'm not going to cover much. Alrighty, so this is showing you the sizes. The reciprocating from the chart. I'm not going to go through it. Different applications for different compressors for different sizes, different usage. But what's important there at the bottom I wrote down is 1 ton equals 1 horsepower, same as 746 watts, 12,000 BTU for high temp, 6,000 BTU for medium temp, and 4,000 BTU for low temp. All right, let's move on now. And so we have also the diaphragm. It's not really used in HVAC. Alrighty, so the rotary compressors are for small AC refrigeration and for freezers. And the hermetic, semi-hermetic compressors for supermarket and factories and big and air conditioners. Industrial and skyscrapers are the centrifugal and the screw. And the rest, scroll and pistons, are for residential, right, commercial AC refrigeration. Alrighty, so now the word hermetic means hidden. It's a Latin word, means sealed. It's hidden. So when we talk about hermetic, it's hidden. We cannot take apart. And we have the rotary, scroll, and reciprocating. Hermetic is welded in a case, reciprocating scroll and rotary. Cannot service, cannot take apart. Now, the semi-hermetic is bolted together. We can service, we can take apart. Alrighty, so these are a bunch of compressors. The one I circles is the one I've seen in my career, and I've seen also Daewoo and Aspera, and other compressors also out there. I worked on these before. Alrighty, now compressor versus the heart. The heart have veins and arteries that plugs up and causes high blood pressure. The heart and the compressor have valves and pipes to move blood around and refrigerant. Both have different blood type or refrigerant type. Dirty condenser and evaporator coil causes abnormal pressure, bad liver or filter, or a clogged arteries, restriction. I misspelled restriction, damage to the heart. Alrighty, so pretty much anything that causes abnormal pressure, clogged filter, dryer, starved metering device, overcharge, undercharge, others. All right, so makes sense how the compressor and the heart are very similar, except one is vapor, one is liquid pump. Now, compression ratio. It's a compression ratio. It's a pressure differential safety range between high and low, similar to human blood pressure. Used to compare the pumping condition for a compressor. High compression ratio can lead to overheated compressor. Alrighty, compression ratio, it is the absolute discharge pressure divided by absolute suction pressure. Explain. Doctors use the blood pressure chart as a tool to determine something wrong with the heart. And compression ratio is used by us technicians to determine if compressor functioning within rated range. Or more engineers use it, not technicians much. Relax, no technician ever have to calculate the ratio, but we must understand it. By maintaining the proper compression ratio, the compressor will never fail. And the compressor never fail. Don't change the video on me. People think I'm stupid. You must think I'm stupid, but I'll explain. Alrighty, so compressor will never fail. First, absolute discharge pressure divided by absolute suction pressure. You have to add the atmospheric pressure. Atmospheric pressure at sea level is 14.696. So calculations now, suction pressure, discharge pressure divided by suction pressure, and you add the 14.7, math, 3.5, compression ratio, 3.1. 3.1 to 5, that's your ratio, this is normal. Now, if we have high head pressure, then head pressure also means discharge pressure. Then what's going to happen to the compression ratio? 4.1, 4.3 to 1. And if we have low suction pressure, also 6.1 to 1 compression ratio. Low in Freon, no problem. We add Freon every 6 months, compressor will break. Don't do PM, no problem. Save money, high pressure, compressor will break. Big problem. Alrighty, don't do PM, head pressure, compressor. Alrighty, now atmospheric pressure. At sea level, the pressure, the air pushing down to Earth is 14.696. Atmospheric pressure drops as you climb up higher. Higher elevation, less pressure. The higher elevation, the less air pushing down. See water levels, water boils at sea level at 212 degrees, 100 Celsius. At higher elevation, water will boil at less temperature. It's hard to boil eggs in Denver, Colorado, I guess. You have to pressure it. So it's important to understand, but not too much, because only if you live in higher elevation, only 1.5% of the population of America lives above 5,000 feet. Denver, Cheyenne, Santa Fe, Flagstaff, major cities. 7% of the world live in above 5,000 feet. All right, so but you still have to do this in case you ever work higher elevation. The pressure is going to be a little different. You're going to go, why is the pressure different? Because now we know why. All right, now, this is only a pressure differential. I did not add the 14.696. This is not compression ratio. This is just the pressure differential. So this is your normal pressure. If we have high discharge pressure, look at that arrow, bigger. We have suction pressure, low suction pressure, and overcharged. Any way you look at it, pressure ratio, pressure differential is going to be different. As you can see, abnormal pressure will affect compression ratio pressure differential high and low. And there goes the RLA. RLA is rated load amp, and I'll cover that later. Okay, now standard versus high efficiency. That's why we replace units, because become more efficient as we go on. Boiling point, let's say now, standard, old school. Boiling point, it should be about 30 to 35-degree colder. So a typical air conditioner should be running about 40-degree boiling point. That's 119 psig. Now the high side on a hot day, on a 95-degree day, we add 30-degree condensing temperature, and your pressure should be 446. Now, high efficiency, we raise the boiling point. It's about 25-degree. Boiling point now is at 50-degree, at 45-degree, 136 pressure. And then your discharge temperature is less now. Discharge pressure is less. It is at 365 because high efficiency runs low pressure is higher, high pressure is lower, lesser compression ratio. So that's comparing standard and high efficiency. There's a compression ratio. There we go. Higher efficiency, lower compression ratio, lower rated load amp, lower watt, and doing the Watt's law, lower the cost. And now with the new technology, ECM, electronic communicated motors, and variable refrigerant flow, even more efficient. ECM power factor 0.6 uses 40% less energy. So with the new ECM and the new high efficiency condenser, high efficiency evaporator, we are lowering costs a lot. And that's why we replace those things. Now in Arizona, 10 to 15 years, you got to replace it. California, maybe 30 years. In Florida, here, we double the size. Okay, now, a story. My dad, when I was still a young apprentice, my dad and I installed AC for my friend's house. And then he said lately, he called me every 2 to 3 years, sometimes on a hot day, it trips the breaker, it's getting old. It's still R22, and it's still working. Okay, and that's why we changed the system every 20 years, 30 years or so, because it's more energy efficient and saves money. Now, for home, it's no big deal, but for it doesn't run too much. But if you have a business, yeah, you should replace it every 20 years. Save money in the long run. Alrighty, let's move on now. That's why we replace stuff. The average temperature in the US, about 80 degrees, to show you how places in the America, HVAC start differently, different part of the world. And like in California, we do more heating because only 78% have AC. Well, my friend in Minnesota, they do a lot of heating up there, even though they do have air conditioners. But my friend in Minnesota, I met the teacher, they teach a lot of heat up there. All right, let's move on now. Now about PM, you do proper PM, things will last. Look at this compressor, it's still running, R22. And this is another semi-hermetic compressor running. And this is an ice machine. It looks like a Vogue. This thing was revised in 2019 and is revised in 1990, revised. So how old is it? Probably from like 1985. Alrighty, so back when I had my business, me and my dad, before my dad retired, long time ago, we installed that freezer in the late 90s, walk-in freezer. And over the years, I replaced the contactor 3 times. We had an issue with the filter dryer restriction later on, but we did PM every year. It's next to a school bus, and the school bus parked there, and then so much dirty that condenser. But as long as you do PM, it's still working. That finally they took it out in 2017 and put a new system because more efficient, save money. Eric, my student, he graduated, went to work, sent me a picture of a Copeland 1950s in Santa Cruz, still working great. Old compressor. I'm not even alive in the 50s. I sent the picture to my friend, old man, and he told me it's from the 50s. So we still have stuff working old. Old customer, Azuma Japanese cuisine, Cupertino, also as machine running, 22 years. Sheraton Hotel opened in 87, my customer for years. Everything's maintained properly. 6 months, had no issues with that huge hotel. The corporate guy from Texas met me. He goes, "Thank you for all the work, Mr. Freeze." And I still have some compressors running from 87 still. Alrighty. And another story about compression ratio, about suction line filter. I'll cover that later. We had compression ratio issues because I go to school, I go to a lot of seminars, and just that same day I took a corporate class and I learned about the compression ratio and the problems because I don't teach stuff at school. So because going to seminars, I became a better technician. Then another scroll compressor, I'll talk about it later. Alrighty, let's move on now. The rotary compressor. The rotary, already. So we have single, twin, and triple rotary. Rolling piston, the motor is cooled by the discharge gas. It's the only freon is cooled by the discharge. Only one valve, discharge valve, and requires a suction accumulator. This one's not used. The rotary vane is not used. HVAC. Okay, so there's a single rotary. You have the twin rotary. You can see two coming in, and the triple rotary, 1, 2, 3 coming in. All right, rotary compressor. We have suction in, suction line in from the evaporator, suction accumulators right there, and this one have dual line in. This is a dual. All right, now the high side. And here is the roller, the crankshaft, the compression area. This is the motor, electric motor, rotor, stator, start and run windings, and discharge condenser. So as you can see, the body is high side. And at the bottom is the oil area. Alrighty, and discharge. All right, the oil is the bottom, low side in, compression, high side, the body's high side. The body high side, the motor cooled by discharge line. Okay, oil at the bottom. Alrighty, now the compression, the compression mechanic. All right, I'm gonna go through this one by one. Alrighty, so power supply to the hermetic compressor. This is voltage in. Power supply to the motor. Now, the motor will start to energize, the rotor rotates, shaft rotates. And then pumps, operations start pumping and compression starts. Compression, suction, discharge. All right, now we have in here, we have this chamber where the compression happens. We're gonna go with one by one. Clockwise rotation. We have the first revolution, fills up with the first revolution, no compression, it just fills up the vapor. And then the second revolution, we'll cover it. First revolution, chamber will fill up with suction pressure, rotation clockwise, 1, 2, 3. As you can see, fills up the chamber. Second revolution, now as you can see, the pressure starts to increase, medium pressure. And the blue is the following cycle. The blue is the next cycle. High pressure, same as the discharge pressure now. Now, the chamber got smaller, squeeze more, and discharge. As it squeezes, discharge. Higher pressure than condenser and discharge. Alrighty, so suction, increased pressure is orange, a little higher pressure, purple, and discharge pressure. So this one is backward, it's coming from left to right. Suction in, as you can see, blue A, B, C, D. Okay. Next. Oh, I'm going the wrong way. All right, so suction in. And now, as you can see, the chamber got smaller, increased pressure. Chamber got smaller, higher pressure, and discharge. All righty, so now, a quick video here. I have videos, I'm not gonna play them, just showing how it spins. I'll post the videos, you can watch them later. Next slide. Okay, so now, and we have the triple rotary. This is the example of a rotary compressor, because it's small, rotary compressor, discharge line, water-cooled condenser. This is water in and out from the water tower or city tower. We have a water tower that cools the water. The water tower is a cooling tower to cool the hot water from the outlet of the water-cooled condenser of the system. I cover it in the water-cooled condenser section, in the condenser section. I'll cover it later. I have pictures of it later. All right, next. There's liquid line out there at the bottom, and then the liquid line out to the thermostatic expansion valve, the expansion valve sensing bulb. This must be an EPR or something. I cannot tell. It's covered. And then evaporator. And then it could be glycol. I don't think it's water. It will freeze. Maybe glycol. And this is the plate. This is a heat exchanger used as evaporator. Alrighty, and we'll cover that more in the evaporator condenser section. All right, now let's move on. The reciprocating compressor, the fun stuff. Reciprocating, first, we have the hermetic is fully sealed. And we have the semi-hermetic is bolted together. And electric motors are inside the compressor. And we have the open drive electric motors outside. Not very common. I only see it once broken somewhere. I'm sure it's out there. They still have them brand new, but not very common. It's a belt-driven or direct drive. At least if you see it out there, you know what it is. All right, so reciprocating compressor. First, we're going to go over the welded cases. It's a good drawing to explain, but it's not correct because the discharge have a muffler and a lot of, it's just a good example of showing how it is. All right, so the motor section, suction valve, discharge valve. This is the motor compression piston section in the black, discharge, and the oil at the bottom in yellow. Right, reciprocating compressors, another good example, boom, boom. Go up and down. Alrighty, next. All right, so there it is. Now, hermetic is welded in a case, welded. Pistons and valve there at the bottom, this one, the crankshaft, spring mount, the motor, suction goes in, the whole body is cooled by suction line. And then the motor is cooled by superheated vapor from the evaporator, compression, and discharge. You see discharge up and down. It's down on purpose because too much vibration, so it doesn't break. Alrighty, next. Now, this one now, it's good to look at the diagram, figure out which one it is. But you can see the suction, the blue are at the bottom, discharge on top. Pictures, it's best to look at the diagram. When you replace a compressor, you replace it with the right one. But it doesn't hurt to look at the diagram. Sometimes they change on you. Every compressor comes with paperwork. All right, now, we have belt drive, electric motor, mechanical from the outside, the pump, and the belt. Or we have direct drive connected by a direct drive connection. Alrighty. Next. Now, semi-hermetic compressor reciprocating. This is the outside view. We have the discharge suction from the back not shown. This is the oil pump and the oil heater, oil side glass. The oil heater goes inside the hole. And we have the electrical head, and the electrical heater is also electric. That's why it's in green. And we have the unloader. This is the electric unloader. We have two. I'll cover it later in the unloader section. Reciprocating. Pistons go up and down. There's the valve. There's the pistons. As you can see, a lot going on. I'm not going to cover it in super details, but I will cover it in detail. All right, this is 3 different examples. Compressor section. All right, so we have the motor here. The motor drives the crankshaft. The crankshaft moves the connecting rod. The connecting rods will move the pistons up and down. The pistons go inside the cylinder. The pistons and cylinder, they pump into the valve plate, and all this in the cylinder head. Now, oil cap, oil flinger. This oil, some have motor, some have oil pump, the big ones. Small ones have a flinger that will splash the oil around as it spins. That's what this is for, to splash the oil. We have Slater and rotor, that's part of the motor. The piston rod and crankshaft, like the other slide. Suction valve, discharge valve, and the head all put together. Now, this next slide, I'll divide this one into 3 sections. The head plate, the crank head plate, crankshaft, piston valve section, oil section, most of the oil in the crankcase, and the motor section. Alrighty. The head plate, the crankshaft piston is the high pressure. The whole body is low pressure. The only thing high is on top. Everything else is low. All right, we have the discharge port and the head are high pressure. We have the valve plate, head gasket, valve plate gasket. Those we can remove, take apart, fix, put back. I'll explain in a while. Suction pressure tab. This is where you check the low pressure. And this is inside here is the piston, connecting rod, and crankshaft. All right, now piston, connecting rod, crankshaft are inside there. Okay, and crankshaft. Alrighty, now the oil section. Over here, this is the oil pump over here. We have the oil pressure tap, oil pump cover, the bearing head, oil pump, oil level side glass. The oil pressure tab, that's how we check for the oil of the outlet of the oil. I'll cover it later. We have the oil drain and the oil sump. And this is for parallel oil. If you have two compressors in parallel together, you connect them, the oil together. And last but not least is the crankcase heater electrical. I covered it in the other slide. Alrighty, oil pressure is the same as the low pressure. And oil pressure tab, the outlet of the oil pressure. All right, now this is different kind of heaters, crankcase heaters. The best one, I guess, the one goes at the bottom there, but that's kind of hard to replace if there's a problem, huh? All righty, and this some idiot put it in the wrong location. Come on, man. Really, oil goes at the bottom. What are you heating up here? The motor? You're actually making it worse. We're heating up the motor here. Great. All righty. Heat travels into cool. You got to remember, on cold days, the oil in the compressor outside is colder. So on cold days, the oil in the compressor is colder than inside. So the freon and oil will migrate to the compressor and turns to liquid. Can we compress liquid? I don't think so. That's why we need a crankcase heater. During the off-cycle, crankcase heater warms the oil to prevent liquid refrigerants from migrating and mixing with the oil during off-cycle. That's why it's important to, when you turn on the air conditioner, before you turn on AC first time, plug it in and for at least 24 hours without turning on so it can warm up the oil. Alrighty. Now the body is the low side. We have the suction port, suction filter screen, rotor insulator in the motor. That's the only thing really important. And the main bearing. All right, now another picture. That's a cool picture here. Suction, compression, and discharge. Next, this is going in more details about the semi-hermetic. That's a big one with 3 heads. So the green is the first suction, light blue. Green is the motor area, compression, and the discharge. A lot of things in the head area, discharge, pistons, and compression. All right. Now, this is inside the valve plate. I mean, the cylinder head. All right. So on top, this is the cylinder head, cylinder head, cylinder head. And this is the valve plate, valve plate, valve plate. You can see it there, all these valve plates. Cool. Now, valve plate. The valve plate holds both the suction and discharge valve and safety relief valves. So there's the suction and discharge valves there. And we have suction valve and discharge valve. Safety relief valve designed to release high pressure side pressure into low side suction when dangerous pressure temperature differential occur. Melted and spring reset. That's the two we have. Self reset as head pressure drops. The spring is self reset. The melted melts. So this is the spring here. You can see it there. I'll cover it next slide. And this one is the melted. This one got heated and melted off. All right, now the melted internal pressure relief. So another story that I'll cover in a while. A melted internal pressure relief valve indicates extreme overheating. It releases high pressure into low pressure when high pressure temperature occurs. Possible causes: discharge valve leaking, liquid slugging, front start, contamination, clogged screen, improper compression ratio, clogged suction line filter. That was my problem. So supermarket customer, Robby story. Also, because I just took the class and the scope of the class, the suction filter was clogged. My compression ratio was bad. Instead of changing $7,000 compressor for $900, I think I replaced the head, all done with. Those prices are cheap. That was a long time ago, back in the early 2000s. All right, so spring, now we have the spring reset type. So the head plate you can replace. Isn't that cool? All right, now this is top of the plate picture. This is the plate removed. The plate is removed. This is under the plate. All right, so and the spring reset, spring automatic reset goes there, goes inside, and you can hear it. Psh, bypass from high to low when compressor overheat. Right. Let's move on. Now let's talk about the clearance space, clearance volume, or clearance pocket. Everybody calls it different. It's all clearance though. Clearance space, clearance volume, clearance pockets. It's that little tiny space thing between the pistons and the valve plate. That little tiny clearance. Is the microscopic gap between the top of the piston and the valve plate at the very top of the stroke. The space indicates how much compression refrigerant we can have and the capacity overall energy efficient. All right. Now, the next 6 slides are super important here. It's showing about the valve plate of the reciprocating compressor, how they work. A, piston at the top of the compression stroke, nothing happening. It goes down. As it goes down, pressure always go from high to low. Now what? The low side is higher than the suction in the piston. So it's going to go down in the cylinder. Number C, bottom of the intake. Now compression from cylinder to high side. Because again, pressure goes from high to low. Now guess what? Inside the compressor is higher pressure than the high side. So naturally it's going to open and go up high. E, and then F back. Alrighty. Now, so okay, let's move on now. Suction discharge valve never open at the same time. It's very important. This illustration is very important. It proves that the suction and discharge valve never open at the same time. Only in position B and D, one of the valves is open. As you can see, look at all these valves. Only B and D, one of them is open. So at any time compressor shuts off, never have bypass from high to low. And that's how we do compressor pump downs next. So, and that's how we check if the compressor is not pumping properly, by performing a compressor pump down. So let's talk about the valves. We have back seat, front seat, mid seat, neutral seat. So back seat, that's how we are home watching a movie, a normal operation. It's open to the evaporator, open to the compressor, and closed to the surface, and a cap should be there. My thing stuck. Okay. Now mid-seat is open to all positions, so we can check for pressure. This is only for service to check it. You can see open evap, open compressor, and open to the gauge to the surface. Front seat compressor. Now to pump down, we close to the evaporator, the one on top. As both these are pumped down in the black box. Alrighty, so the front seat, I'll explain next slide. That's how we check. We close on the evaporator and pump only in the crankcase of the compressor. Compressor pump down. Run compressor to half a PSIG at stop. The pressure should not rise. Possible a little bit because of warm oil causing the freon to rise. Correct? Pressure to rise. Pressure to rise. If rises pressure, try again 2 or 4 times. If continue to rise, we have a bad valve. If it's a semi-hermetic, open it and let's see it, fix it. It could be just a broken valve. Could be something minor. All right, now compressor pump down, troubleshooting. So now backseat normal operation. Right, it's open on both sides. Pressure evaporator 18, Pressure going to the valve 18, 18, 18, and discharge. And we have the gauges, but it's 0 psig because it's still closed, but still in the backseat position. Now, to pump down, mid-seat position, we turn it clockwise 3 or 4 turns, just a little bit to get the pressure. Now we open it. Well, we should get some kind of pressure now on the gauges. There we go. Now we have pressure on the gauges, 18 psig, same as system pressure. Now, front seat, so we can pump down clockwise all the way. What's going to happen? The compressor is going to pump down and suck all the way to half psig and stop, because it's going to pump from the valve to the compressor. And the Freon is located from the discharge line. Now, the system of the Freon is only from the discharge line all the way to the condenser, to the metering device, evaporator, suction line, and stop at the valve. So inside the compressor is empty, half a psig. All right, Freon from discharge line to metering device, evaporator, suction line. All right, compressor is crankcase, low side isolated. But remember, only the crankcase, we still have pressure at the discharge side of the compressor. Now, compressor slugging. Let's talk about slugging. Liquid made the Grand Canyon. If liquid can do this, what do you think is going to happen to my piston and my valves? Slugging is a dangerous process where liquid, refrigerant, or oil enters the compressor. It's a vapor pump. Vapor, misspell. Vapor pump ruins the valves, broken internal parts, and compression. We cannot compress liquid, very important. I don't care if it's titanium alloy. You cannot compress liquid. Alrighty, how you like that? Flood back. Thank you, Emerson. Emerson that make compressors. Couplet compressor, this is a video on YouTube. The guy took apart a compressor. How you like broken piston? How you like that? You think liquid slug back? Of course. Oh, this is a discus compressor. You can tell from the valve plates that it's circle. And broken piston, broken crankshaft. All right, and speaking of discus compressor, there are a new style now. Discus compressor have more efficient ratio because less clearance volume, clearance pocket, has larger bore to allow more gases through within period. So that's a discus compressor. Now, let's talk about unloaders. Compressor unloaders, they go from the outside, they unload the head. Unloaders are mechanical or electromechanical device that reduces the compressor's capacity, temporarily preventing some of its cylinder from compressing. This allows system to match cooling demand, prevent short cycling on and off. Short cycling, thermostat calls for cool. This is the example. Thermostat calls for cool on a hot day. Room temperature 95, no problem. But in a cold day, room temperature 72, low temperature equals low pressure. At full capacity, the compressor will suck too much and cycle on off on low pressure safety and will not work properly on off too much. So we need unloaders. Unloaders controls the capacity of the horsepower of a compressor. Now, electronic unloader energized by voltage, no voltage on the left, no voltage, valve closed, suction goes into the cylinder, piston compresses and discharge normal. Voltage applies to the coil, opens, and high pressure closes the valve, no suction. You can see now one of the valves is circulating around, is not working. One of the valves is not moving. And we have the automatic unloader. It works on pressure. And it's the same thing, but it works on pressure. Alrighty. Same thing with unload and unload, and you have adjustment screw on it. This is old school. Now let's move on and talk about oil system. Alrighty, so light blue, superheated vapor from the evaporator. In this case, light blue is vapor refrigerant, and the red is oil. And red is oil. And there's the oil pump. Oil pump moves the oil everywhere. And some of the oil also goes, oil discharge with the hot gas. Oil comes back with the suction vapor also. Oil is in the system everywhere. All right, oil level. Now we have the couplant K body, oil level. The discus compressor had need more oil, I guess. And the D4, I need less oil. I guess the body's so big, you don't need that much oil, plenty in there because wider. Those things keep changing. When I was a student, first it says doesn't matter as long as you can see any oil. Then they said it should be 2/3 to 1/3, and they keep changing on us. All right, couplant oil pump. There's the oil pump. You can tell it's an old compressor, but a new pump. And Emerson oil safety control. Oil pressure differential, usually 30 to 60 above suction pressure. Oil pressure, oil suction pressure, same as low pressure. So we check the oil pressure to see something is wrong. We don't check it unless there is an issue with the oil control. And we have the electronic oil level regulator. Okay, now oil control. I'm going to cover this in details. We have two kinds, the electronic and the regular. Bunch of diagrams. Alrighty, more diagrams, cover in details. Alrighty, so an oil pressure control or oil referral switch is safety. The differential between the oil pump pressure and the suction pressure. It turns off the compressor contactor coil if the compressor loses oil for a certain time. It's about 90 seconds. I'll cover it in details. Now look at this diagram. How can you make any sense out of all this? But one by one. All right, so normal operation right now, system is off. Power comes in L1 through the oil control, normally closed switch between M and L, but does not turn on the motor because the operation control is open. Now, calling for cool closes. We have power to the compressor contactor coil, creates a magnetic field. We'll close the switches. Now we have power L1, L2, L3 to the motor, and we have L1, L2 going to the heater, going to the oil control. Now, if we have a problem with the oil, heater turns on after a certain time, usually 90 seconds, but the cover must be on, because if you take off the cover, that heater will never get hot, will never work. Then, oil pressure differential, usually about 30 to 60, the suction pressure, 30 to 60 above suction pressure for about 90 seconds. That's the oil pump pressure. And then, so what happens is then, if when it opens, close. Now opens, no more power. It will cut off power on the contactor. Now to check it, the voltage is the electrical pressure differential between pole A and B. Right. So if it's open, we should have 240 volt. If it's open, we should have 240 volt here between the M and L because it's open. We're reading the blue and the red line. Now, on top, L1 and L2, we should read 240 volt because we're reading L1 and L2. But now the control is closed. We're reading 0 volt because we're reading pressure differential between L2 and L2. Again, voltage is the pressure differential between point 1 and point 2. So if you're reading the same line, it's going to show 0. It's not 0 volt. We do have voltage. We just can't measure it. It's very important to understand this, okay? On the left side with the resistance, 0 ohm, 0 ohm, and we have high ohm shows you it is the heater. Now this is closed, that's why it shows 0 ohm. Maybe it's confusing, this one. All right, let's move on now. Oil control for parallel compressors. This is an example of oil. We have multi-evaporators with EPRs, and we have multi-condensers with fan control headmaster also. It's just imagine 3 big compressors for just 2 small condensers, and also liquid receivers and other good stuff, suction filter. All right, first we have the oil separators there at the bottom, oil pressure regulators, 1, 2, check valves. We have the refrigeration check valve, and the oil check valve, discharge check valve and oil check, oil reservoir and differential pressure, oil filters, oil filters. All right, now from the discharge line to the oil separator, first oil comes in. Follow the arrow. System oil comes from the system. It goes into from the discharge line to the oil separator. And then goes out to the check valve, oil check valve, some of the oil to the liquid line. Okay. And then goes to the check valve. Now it goes, some of the oil small there goes to the liquid line, and most of the oil goes to the oil reservoir. Now, the oil reservoir filter, now back, oil reservoir, it goes to the back to the filter. And back to the oil pressure regulator, back to the compressor. And then we have the oil pressure differential. In case the pressure is too much, it will release some of the pressure back to the low side. All right, that's how the oil system works. All righty. Now, stuff you see online, this is something new I saw. I'm sure it's out there somewhere. It's called oil injection. Old school. All this is old school. So this is oil injection system. Saw it online, but I don't want to cover it too much. All this is old school, all this oil, because I'll cover it later, why old school. Scroll compressor. Now let's move on to the scroll compressor. More efficient than the reciprocating compressor. No valves, fewer moving parts. There's no clearance volume. Two spiral scrolls fit inside one another. All right, suction port, discharge, outlet, discharge valve. Stationary fixed scroll attached to the body of the compressor. And the orbiting scroll, powered by electric motor. And there's the scroll. All righty. The blue one is the one that moves around. The red one is the fixed. Okay, another examples of the discharge, a lot of videos on YouTube. All right, so I'll show this by example, one by one, all these. All right, now again, the high side discharge on top, low side, and oil at the bottom. Similar to the rotary. Similar, but nothing like the rotary. All right, so, and then look at this big old compressor and a small little tiny condenser, small metering device, and a small evaporator. Okay. All righty. Now, we're going to cover this one by one. There's a cool video about this here. So we have the fixed orbiting scroll, discharge port, and suction port. A, rotation clockwise. A, must be Canadian, huh? All righty. All right, so compressed gas in yellow. Superheated vapor from the evaporator comes in. We have a big gap, clockwise. We have higher compression, orange, smaller gap. The other one is the B gas, different gas coming in. Now the A gas, discharge pressure is red, more smaller gap. The B gas now turning orange. And then we have the C gas entering in. Now the A gas, very small gap and discharge. Superheated vapor from the compressor. And the B gas and the C gas and the D gas. Okay. Sounds cool. So the scroll, capacity control modulation method. We have two-stage modulation, 2/3 capacity and 100%. Customized scroll with variable frequency drive. Mechanical modulation. Stepped capacity, infinite capacity. I'm just going to cover the first one. Two scroll modulation. It is by mechanically unloading a compressor, it operates at 2/3 capacity or 100% capacity. Utilize a three-way solenoid valve to pressurize lift the chamber. Offers improved temperature and humidity control. a 2 to 10 horse, ideal for 14 SEER residential and light commercial split air conditioner. SEER stands for seasonal energy efficient rating. Now, part loaded. I'm not going to go in details with it. Two-stage compressor operate 60%. The modulation is based on time. The computer tells it when to open and when to close, and it works on time. When the solenoid valve is on the compressor is unloaded, a portion of the gas is bypassed back to the suction port. The motor is always the same speed, but the effective displacement, it reduces the volume of the scroll when it turns. So high stage 100% capacity at full load, thermostat signal and internal solenoid motor to energize. So okay. Motor is always fixed speed and low stage and high stage. Now, these two slides shows how it comes on and off in second. So if you go to a job site and here it comes, you know, it's normal. That's how it's supposed to be. So example, cycle time 20 seconds. 20 seconds is the total cycle time. 10 second on, 10 second off, loaded 10 second, unloaded 10 seconds, 50% modulation. Well, another example is we have 20 second total. All right, 8 second on, 12 second off, 40% modulation. All right, now let's move on to the screw compressor. The big one, cooling jacket. The motor rotors, the two rotors, anti-friction rotors, timing gear, shaft seal. And there's a cool video about it also. It's a cool video. You can watch it on your own. All right, and Centrifugal also have a cool video also. I'm not going to cover Centrifugal much. All right, now, speaking of the scroll, my friend and I go into concert. I was back home, California, visiting family and friends, and going to San Francisco for a heavy metal concert, of course. And then my friend goes, Robby, stop by the computer company my friend works at. I met him in college. I'll give you a tour. So finally, went to see a tour. There we go. They have 4 compressors. This is a 17-story building. 4 compressors, 4 discharge pipes, the discharge lines, 4 suction lines. Now there's the evaporators, and it's a very dry day because barely any water coming out of the evaporators. Now down here is the 2 filter dryers, the system running R134A air conditioner, and 2 liquid lines. 2 liquid lines going to the TXV, 2 discharge lines from the compressor. And this is the water tower to cool the condenser. And 2 side glasses for the 2 systems. This is the blower wheel to move the air to cool. Controllers, we have compressor controller. It's the same controller, but you push a button, evaporator or compressor. 6 evaporators total, 4 compressors, 2 systems. 3 evaporators per system and 2 compressors per system. All right, now it says compressor 1, amperage 97. So the whole building is pushing, not only 1 compressor running. So. Or I guess what they mean by compressor 1 is 2 compressors, because 2 at a time run already. So, oh no, this is system 1 compressor running. Anyway, whatever. So what I mean by saturated temperature, that's probably the air exiting the evaporator supply air. That's probably they mean, because it's not saturation temperature and the evaporator is not 56 degrees, no way. That's what probably this means. And then saturation set point 55 sounds right. And then outside temperature 69. And compressor 1 discharge 131. And suction pressure 31. Using a PT chart, boiling point is 36, all righty? Because we know pressure is 31, 31 equals to 36 temperature. Correct, boiling point should be 36 in air conditioning. So air is about 70 degrees, boiling point 36, that's delta T of 34, evaporator 34 degree lower than the building. Excellent. Outside temperature 69, condensing temperature 103, delta T is 34, condensing temperature 34 higher than the outside air. Okay, sounds right. 100, it says here, back here, one discharge PSI 131. The discharge PSI 131 is about 102, 103. Alrighty. Since we are in this building, we also have water-cooled condenser, water pressure regulator, water-cooled condenser. For this is probably walk-in freezer, it looks like. Yep, walk-in freezer because suctionized insulated. And then all this is cooled by the water-cooled condenser. Water tower cools everything. All right, so all this is old school, old school, old school. Now we have the new oil-less system my friend told me about. Compressors with magnetic bearing, no need oil. And of course, using electronic expansion valve. I can't imagine how efficient it is. My friend told me the compressor have an oil safety control to shut off if any trace of oil. How you like that, huh? New technology. That converted another building to the new oil system, oil-less system, and it took forever to remove all the oil. He told me compressor keeps shutting off on oil safety, too much oil in it, any trace of oil in it. So it's amazing how much oil there's in the system. This is the new technology moving on. Alrighty, rotary compressor. Rotary can use any kind of freon. Two matching scrolls that move around. All right, we have female and male gear. One goes clockwise and one goes counterclockwise. And then vapor refrigerant enters, suction, compression, and discharge. Similar to the rotary and the scroll, but it's two that spins. Okay. And we have also two-stage compressors. I never worked on, only in books. There's more going on. We have low pressure cylinder, high pressure cylinder. We have temperature sensors, liquid injection TXV, liquid subcooler, and suction separator. I think they mean by the suction accumulator, maybe, probably. But I just put it in there so if you see compressor with 4 valves coming out, 4 pipes coming in and out of it, then you know it's a 2-stage. That's for ultra cold freon. Alrighty, 2-stage. Now, while compressor fails, let's go to troubleshooting. All right, high head pressure, airflow issues, head pressure, oil issues, acid, heat issues, slugging, evaporator, air issues, evaporator airflow or TXV issues, crankcase heater issues, crankcase heater, compression ratio is high or high pressure, overheating, oil issue, lubricating problem, contamination is moisture issue, and no preventive maintenance will cause all the stuff. None of these electrical problem, because electrical is not a problem of causes, only if it's wired wrong or we have power surge. A relay capacitor overload will never cause a compressor to burn. We have protections. Now, let's talk about under warranty and let's talk about problem and cause. They estimate 50 to 70% of compressors under warranty, nothing's wrong with them. So most of these problems, because the root cause of the system issue, rather than the compressor itself. When the actual problem isn't fixed, the new replacement will fail. Copeland, often report that many units sent back are no trouble found or could not duplicate a fault. Now, the problem and the cause. Problem is the, for example, problem is the symptoms. Right? Example, broken compressor valve. The cause is the fault that caused the created the problem. Example, dirty evaporator, bad airflow, bad expansion valve will cause broken valve. And that's a story for you. A service technician must fix the problem and find the cause of the problem and fix it. Fixing the problem without fixing the cause, the problem will occur again. That's very important. That's why we're technicians, not mechanics. A mechanic fixes the problem, finish. But a technician gotta figure out the cause of the problem. I hope it makes sense, right? Now, quick story, a liquor store next to the football stadium there, and there's a football game going on. Walk-in cooler, the compressor trips the breaker about 4 to 5 times a day. How do you like that? The customer told me they replaced the compressor, potential relay, capacitors 2 times, and the contactor, and still trips the breaker. 3 companies looked at it, and nobody can figure it out. The current was going up, increasing as the suction pressure going down, decreasing. So something's wrong. Top of the hermetic dome was harder than usual. It's a bad new compressor? I doubt it. But the resistance is okay. Common run and start is good. Electrical okay. I follow the power all the way to the breaker and the breaker running hot. There we go. I only had 8 amp running through my 30 amp breaker. Why is that hot? Loose screw connection on the breaker. If we have an 18 amp draw on a 20 breaker, then yes, it's supposed to be hot. So regular standards, according to the regular standards, a breaker should generally be at maximum 122. That's if ambient air is 75. So that sounds right. My breaker was running about 150, 160. And outside in Santa Clara, California, temperature was like 70 degrees. And there we go. The standard breakers that run about 122 degrees. So 150 degree hotter than the ambient air. So run about 94. So a lot of things you can figure out by the laser gun, because I understand electrical theory. It was just 2 loose screws. That was the problem. People replacing compressors for no reason. Now, RLA versus LRA, rated load amp versus locked rotor amp. Rated load amp is the normal running. Locked is a temporary amperage before it starts going. That's locked. And then you can see here, it shows the amperage. It shows the locked. There is no exact formula to convert. General rule of thumb. Formula is 5 to 7. The locked amperage is 5 to 7 higher than the rated amperage. The rated load amp is a steady current of the compressor under normal condition. And locked rotor amp is the initial high surge current on the compressor first prior to start when the rotor is locked. All right. Let me pause here for a second. Look at the small screen. So this is locked. This is spinning. All righty. Now, it takes 7 times harder to start. It takes 7 times harder to do this than to move. It's very important. Okay. That's what we had to learn in school, believe it or not. Now, a lot of useful information in the Copeland book or the TechMC book, whichever manufacturers. Potential accurate relay pick up a drop-off voltage. I'll explain that. I'll explain this one later. And we have the resistance is nice. We have the part number. Overload, or sometimes they call it Gardet. You know, I heard it called Gardet. And the microfarads, maximum RLA, and Lox rotor amp. Now, I did the calculation for fun to see what's going on. So long story short, I just divided the Lox rotor amp by 6 so I can get the rated load amp and make it easy to see if it works. They never tell you the rated load amp on the nameplate. Only the compressor book have it. So I use the formula, and most of the time the RLA is within 5 to 7 times lower than the locked rotor amp. So that it says maximum. So the first one must be a typo. There's no way 2 and 20. I mean, come on, compressor 10? I don't think so. So only 1, 2, 3, 4, 5 are not within the range, are not between 5 to 7 times. The rest are within 5 to 7 times. How you like that? Isn't that cool? So kind of works. Now, for 3-phase, there is no formula. There is a formula, I mean, but you don't have to do it. Trust me, 3-phase is a lot easier than you think. 3-phase is easier. If it's not at locked rotor amp, then it's locked. We can try to reverse polarity and break it lock by the scroll, but you could not reverse polarity on the scroll. If it's locked rotor amp, something's wrong with the voltage, or if it's not at locked rotor amp, something's wrong with the voltage or compressor winding. All right, so another story here. 5 AC. Oh yeah, at Pedro's restaurant, Los Gatos. 5 AC's down. Okay, they call me up. Robby, she called me up. Cairo manager. Robby, 5 AC's broken. I go, what the hell? 3 are brand new, man. 3 are less than 4 months old. We replaced on my company, and 2 are older. Our older one from the 80s. As soon as I parked, I can tell the scroll compressor running backward because of the sound. Electrician doing work and reverse polarity. The new unit had reverse polarity on the compressor contactors, and everything else single phase, all the old units. How you like that? The old unit had reverse polarity on the evaporator blower, the condenser motor single phase, and the old compressor 3-phase reciprocating. So the old compressor reciprocating, I don't care if it spins clockwise, counterclockwise, it's still gonna go up and down, doesn't matter. The problem, a lot of things I fix after electricians, it's crazy. Fixing after electricians is not very unusual. A lot of times I fix after electricians all the time. Alrighty, let's move on to troubleshooting. All right, so average reading is in green. Normal 30C, this example it says this. So 30C is about, I would say, AC room temperature. 30C is about 75 degrees. So 33 about 78 degrees. All right, so here on the left, we have condenser airflow or overcharged, and both pressures are high. System low in charge, both pressures are low. And weak compressor, high suction, low discharge, weak compressor. But you gotta look at the amp draw to make sure. Now, we have a lot of arrow charts. There's your weak compressor. And look at your amp draw, low suction and low, both low. So check it out here. The low pressure is low, and low pressure is low, and we have low current amp draw. Down here, high pressure is low, low pressure is high, and we have also low amperage because compressor is not pumping. Low amperage, low amperage. You can tell a lot from the current draw. The mistake everybody makes. I do not start my compressor without my clamp on meter, people. On Facebook, all the time on Facebook, people taking pictures of a gauge. What's wrong with the system? And nobody tells me the amp draw. You gotta know the amp draw every time you turn on the compressor. You can tell a lot. Alrighty, so not everything's correct online because you can see those things don't match up. Okay, not everything's correct online, but I found one that is correct. And this is split in 4 places: 1, 2, 3, and 4. And this is how to make adjustments: TXV, EPR, CPR, and automatic expansion valve. All right, so the correct arrow sheet should show both TXV and fixed metering device, fixed bore and TXV, because it changes a little bit in the superheat. Superheat changes normal, and here it changes. So you have to be careful when you look at the internet. A lot of things are wrong. Alrighty, let's move on to electrical now. 3-phase wiring. All right, so we have delta connection. And according to this diagram, you can see L1 connects the 1 and 7 with the L1, and 2 and 8 with L2, and 3 and 9 with L3. Now, this connection, we have the L1 to 1, L2 to 2, L3 to 3, and 7, 8, 9 together. They go nowhere, just together. Now, in some cases, we have delta start, star run. Big compressors, kind of 3-phase compressors, some of them are too strong. They need the delta connection to start, and then they switch to start connection. So there we go. Delta connection over here, start connection. All righty, let's move on. Okay, so you can have a 3-phase motor running with a single-phase power source. There's also a story here. But it doesn't work for compressors. Okay, so a student of mine, Geraldo, with me at the food pantry, customer I had for years, emergency housing. I worked for the homeless shelter. I had different locations, customers. And the walk-in cooler is out because the contractor ordered 3-phase compressors, but we don't have 3-phase power to the building. So that installs variable frequency drive. Stupid. So we replaced the burned 3-phase to a single-phase 220 because it doesn't work. So the 3-phase, it adds one more phase for the 3-phase. It's fine for the motors, but it doesn't work for the compressors. So we replaced the burned 3-phase to a single-phase 220-volt and bigger size wire, bigger breaker, and contactor. This was installed less than a year ago. The customer did not want to go through the other contractor anymore. Geraldo and I ended up replacing both walk-in coolers and freezer compressors. I charged the customer for 2 new compressors, but I returned the 2 3-phase and got 2 under warranty and gave it to the customer maintenance department. I ended up installing it at a different location somewhere else. So not on compressors, this one. You cannot use variable frequency drive on compressors. I mean, variable frequency, it adds one more phase. Alrighty. Now let's move on to the potential relay, current relay, and PTCR. A lot of videos out there. All right, potential relay. I call them electrical starters because you tell the customer, I replace a relay, there's $150. They're gonna go crazy. $150 for a relay? Well, it's not just a regular relay, it's a potential relay, okay? All right, let's move on. Potential relay, we have 1 and 2 is the switch, 5 to 2 is the coil, and 4 and 6 is dummy, doesn't go to anywhere. All right, we have so many diagrams for potential relay. There's one diagram, there's another diagram, another one, another one, another one, and another one. There's more. They're all different diagrams, but they're all exactly the same. All these are the same thing, just different ways. But some they forgot to add the overload on 3 of the diagrams. They forgot the overload on there, and there. It's amazing. And that one from the factory, that last one here, the bottom right, that's from the book of the Tech of Copeland. And the factory forgot about the overload. Alrighty. So example, power in here, power in, and power in. compressor terminal here, and compressor terminal here. That's the easy part. Now, run capacitor, and run capacitor, and start, and start capacitor, and your potential relay, and the potential relay. All right. I will use two of these diagrams to explain the sequence of operation. I'm just going to use these two only because it's too much to use all. All righty, so sequence of operation 1 and 2 is a switch. Power comes in, but now control is open. Switch is always closed between 1 and 2. It starts with closed. Power goes in now, contactor is closed, power goes in. There we go. First goes to the run windings. Okay. Then, also, all this is first second, and power also goes to the start winding and to the normally closed switch and out to the start capacitor and out L2. All right, that's first second. And in the first second also, power goes into the relay coil and out. That's what's happening in the first second. Now, second, relay coil EMF switch will open. Now, see the switch? The switch will open. Switch will open. Now, when switch opens, as you can see, power only goes between the run windings. Because power only goes in the run windings, the back EMF, the start winding will create its own back EMF, and that will cause compressor to hot, and we have run capacitor to slow down. So that's normal operation. There we go. L1 to R, and the run capacitor between R and S to slow down the electrons. All right, this is top view. Thank you, refrigeration training. I met them in Vegas. They gave it to me. Coil, contacts, common from the compressor terminal, from the run terminal, and to start terminal. And those two are dummies. They go nowhere. There's a relay coil, normally closed, 1 and 2. Closed. Okay, now, after startup, coil energized. 1 and 2 are pulled open. That's the difference, closed and open. All right, now potential relay, the potential relay goes in the box next to the compressor. And we have the universal relay. It's a universal relay. You can adjust the pickup voltage. It's nice, but I don't trust it on some aromatics. Alrighty, it's a cool little thingy. I have it in my truck all the time in case I need it. And guess what? 2 more diagrams. There we go. 2 more diagrams of showing exactly the same thing, but one of them doesn't have overload. It looks like, yep, that one doesn't have overload. Capacitor start, capacitor run. The same thing as a compressor. But overload missing. Alrighty. Oh, that one have internal overload. That's right. That one have internal overload because it's inside. Must be an air conditioner. Alrighty. Now let's move on to the current relay. Most current relays snap into the start and the run terminal of the compressor. You can see it snaps in there. There we go. But this relay, it goes in a box with the capacitor outside of the compressor. Right now, current relay, almost the same diagrams. Look how many we have. 1, 2, 3, 4, 5, 6. All right, but this one have no capacitor. This one have no capacitors at all. That means compressor start, induction run. This was no run capacitor. This one have optional run capacitor. It says it's optional. This one have no run capacitor. And this one have no run capacitor either. Most of the time doesn't have run capacitor, most of the time. Right, and almost the same diagram, but a little different because some start capacitor between relay and compressor. Look at the start capacitor between 5 and 2. Well, look at this start capacitor. Start capacitor is between 5 and 2. Oh, they are the same. Sometimes I see a different place. Oh, this one here. Oh, that one here. Start capacitor is different location there. I have the wrong one. Yeah, correct. That one on top is the one no box is start capacitor, different location, but it works same way already. All right, and this one start capacitor before the relay. All right, now current relay, overload, and capacitor. So current relay, common start, common and run of the compressor, and S&M. Okay, S&M overload, start, common, run. This is that picture. Let's move on. The overload. SM, there's 1 and 2, 2 and 2, 1 and 2. One of these up there should be 1. I misspelled. All right, next, overload. Look at these burnt wires, bunch of overloads. Current relay switch open, overload, start winding, run winding, start capacitor should be all blue. First step, second, power goes through L1, from L1 to overload to the common windings and out through the start windings and the coil relay. This is one of the few times where in the HVAC where we have two loads in series, the coil relay and the compressor relay in series. Second, now the coil will create a magnetic field and the switch will close. Remember, switch open and power goes through the relay coil. Now switch closes now and power goes through the start winding. Now the relay will open and continue to run only through the run winding. So first it goes into, switch is open, it goes to run winding first, creates a super high amperage. That's why it's called current relay. High current will cause the switch to close. When the switch closes, we'll turn on the start windings. And start windings, now the current will go down and will open. All right, that's how it works. And the start windings out of the system. And the start winding and the current relay out of the system. Relay coil. Actually, relay coil is still in the system. Only that's misprint here. Only start winding out of the system. Okay. Terminal and current relay. Power goes in common jumper wire, but this is reversed. L1 goes to the L1 goes to the overload and neutral goes out. And remove jumper cable to the start capacitor. Alrighty. Current relay, power in, relay coil, power out. So power goes into the coil and out. Jumper. And to start, energizes, start and run windings, voltage through the coil, and out to the main run windings. High starting current, increase coil magnetism. Plunger closes. Power to start winding. Now it will de-energize as motor speed increases, amperage falls, and opens. All right, now the split phase motor with current relay, no run capacitor. This is same thing, but different way of looking at it. Power in, common through the relay coil out to R. We have high starting current. Switch will close. Power will go through the start winding. And when the current goes low, opens. Same thing, just different way. And power continue to run winding, run and normal current. All right, now let's move on to the PTCR, positive temperature coefficient resistor, and PTCR and the potential relay. Oh, this potentially, okay, forget this line. All right, now I have a pop quiz later, but first we cover the PTCR, potential relay, current relay, and PTCR. Positive temperature coefficient resistor. It's not a relay, it's a resistor. And we have some with 3 wires. I can't find a diagram to 3 wires to explain how that works. I don't remember. I've seen them before once or twice, but I can't remember right now. But they do have 3 wire. You just look at the diagram, you can figure out what they do. Alrighty. Now, how they work is power comes in L1 and out to run. Okay. And also start because the PTC is closed, right? And start capacitor. Now, and out. Now, PTCR gets hot and opens. So when it opens, no more power in the start winding, only run. It's pretty simple. All right, now, pop quiz. What is in parallel with the run winding, in series with the run winding, or in series with the start winding? It's pretty simple, right? A, B, C. So A, right? The potential relay is in parallel with the run winding. You can see run winding is here and it's parallel with it, with side by side. While the current relay is in series with the run winding. And the PTCR is in series with the start winding because it takes the start winding out of the system. They all do the same thing, just different ways. Alrighty. So a lot of things are totally wrong online. Look at this idiot have somehow run capacitor and start capacitor together. Look at that. Alrighty. Don't believe everything you see. And this is from the book, and it's also wrong. From the book. On single phase compressors, the order of the terminals are CSR. That's not true. That's not true. Okay. So we have standard electrical connection, compressor connection. They look the same, but a little bit different. This is a good connection. Make sure no issues. Is this good, boss? Broken compressor? All right. So one picture is the wrong way to check the resistance. All right, which one's the right way? Which one's the wrong way? Use alligator clips. This thing is so tiny, your hand moves. You gotta use alligator clips to check for resistance. All right, now let's talk about 3-in-1. 3-in-1 relay is used to start protection on older, not old, on also new refrigeration or freezer, also AC. All right, so many things are wrong here. I Googled it. It's YouTube. Strictly good by compressors, horsepower, and voltage. So voltage 150. I've never seen 220. So horsepower one. Well, they have 3 kinds. The 12 to 5th quarter and a third, and only half. All right, and here it shows third to a half. No, only half. But the half have mistake also in the half because the half they all look the same. Okay, and the half have a small little connection like the third and the quarter and the 1/5. So the half need a different connection. Every time I gotta cut the wires, I put a different connection. Idiots from the factory, they made the half finally after a while, finally came up with a half, but not the right connection. All right, big mistake by the manufacturers again. How come I'm the only one who sees mistakes here? So the mistakes is this. We have black, 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 white, red, black, black. Which one is neutral? Alrighty. Where the overload should be in the black L1 or white L2. The overload should be in the black. So there we go. This should be white. I can't believe people make that mistake all the time. So before I install these babies, I get my own meter. I ohm out. For safety, I always install white tape on the black wire to know this is the white. I ohm it out, right? I ohm out the resistance. And between the white, one of the blacks and the run should have resistance, right? Because that's the run winding. Okay. Now let's move on. This is the universal relay. This is since we're talking about capacitors and stuff, this is some ACs, simple, no relay, no nothing, just capacitors. This is a picture of a dual capacitor in a diagram. If it's burnt, it's bad, possible bad potential relay. Most of the time, if it's a burnt capacitor, it's a burnt potential relay. If expanded, it's bad. Look at that, expanded. All right, now, system failure and 4 causes of compressor failure. All right, so electrical failure. Okay. We have capacitor failures, contactor problems, wiring issues, refrigeration leaks, overcharge, undercharge, blockage. We'll get to that later, I guess. Mechanical failures. We have seized compressor, worn. So mechanical problems, either broken valve or not pumping. Electrical problems, either short to ground or short to itself. But there is one more, not in books, very rare. It's called a partial short. It happened to me a couple of times. And up there, mechanical, also airflow, worn out belt, and others. All right, now, Robby's story. Ice cream cake display, a Nirvana Persian ice cream in Sunnyvale. Customer lost 2 expensive ice cream cakes. The breaker trips 2 to 3 times a week. Okay, very rare. When I arrive, compressor is cold and the system's off. I turn on. Everything checks okay. Perfecto. No issues whatsoever. Okay, maybe it's a fluke there, boss. Next time it trips, I told the customer, turn it on an hour before I arrive. So I call him up. Hey, I'm coming. Turn it on. I arrive. It's hot now. The amperage increases. The amperage is increasing as the pressure increase. I'm sorry. Amperage increasing as the pressure decreases. And we have a small short, with itself. So then I check the common run start, and it's not fluctuating. I probably serviced over 1,000, 10,000 compressors in my life, and only happened twice. Sheraton Hotel and that Nirvana ice cream. But at Sheraton, the compressor fell. That was bad. I added I added a run capacitor. Amperage dropped by 1 amp, but it didn't work. So it only happened twice, very rare, but we do have a partial short, right? They say broken valve or seized, locked, short to itself or short to ground, but we also have a partial short. Very rare, but it could happen. Alrighty. All right, now let's move on. Single phase compressors. So we have power in, and power in continues to the wire nut. Power goes to the screw, the overload screw, and power from the overload out to the common terminal. Power to the compressor in the red, and power goes to the pressure control, and power from the pressure control, red wire, and goes to the run terminal. Okay, now in the run terminal, it goes to the fan, and the common goes to the fan. That's 220 to the fan. And power to the common run and yellow, black, red, and yellow goes to the electrical starters. Okay, and the only thing yellow is back from the start winding, power from the yellow to the start winding from the start relay, from the current potential relay, All right, now let's move on. Run windings, start windings. So run winding should always be the smallest winding, 2 ohms. The start winding. Okay, this is not working here. How about there? Okay, here we go. So better this way. All right, so as you can see, between common and run, we have 2 amp. All right, and the one on the left, start and common, we have 8 amp. Total is 10 amp, 10 ohms, That's how we know if it's working, if the resistance is proper on a single phase motor. Alrighty, so common and start plus common and run should equal to start and run. Hope makes sense. Now, three-phase compressors. Please ignore the ohms. Some idiot online thinks it's a single phase. Right, these numbers add up. 0.8, 3.2, 5.4. They add up, but if it's single phase, you can tell it's a three-phase by the overload. It's a three-phase overload. I mean, come on, man. So many idiots out there. All right, another example of three-phase. So now this is three-phase motor windings. So between this connection, and this connection, that's one of the windings. Starts here, ends here. The other winding starts here, ends there. And the other windings, blue, start here. They meet in the middle of the overload and meet at the overload in the middle. Okay, so now three-phase compressor with open overload. If the overload's open, you're going to have 0 OL. 0 OL, any one of the legs. Overload open, all three legs at the same time. It's a three-wire overload. Okay. And now single-phase compressor motor windings. Or three-phase. We're back to three-phase. Three-phase, power in here. L1, L2, L3. It connects to the motor and back out other side. And the same line. 1, 2, 3. Overload electrical plates removed. Terminal starts, terminal ends. Overload goes there. Okay, this is it. The rest is all review refrigeration. Thank you for today. And expansion valve next. Thank you for today. Happy New Year. And peace. Leave a note. Let me know how I did today with this presentation. Have a wonderful day.